Students, the objectives of today's lecture will enable you to understand the concept of resonance energy, which leads to stabilization of benzene, reactivity of benzene, and reactions of benzene. Let us start today's lecture with resonance energy. Students, the resonance energy of a compound is the measure of extra stability of the conjugated system. Means, from conjugation we have brought a conclusion that conjugation leads to stability. But resonance energy is the energy which is going to describe the extra stability than expected as compared to the corresponding number of isolated double bonds. This can be calculated from experimental measurements. For example, benzene is 36 kilocalories per mole more stable than a hypothetical system, and this is called the resonance energy of benzene. Let us try to understand this concept. Students, let us calculate the resonance energy of benzene through an experiment. Now, this diagram shows the experimental heats of hydrogenation, means the amount of heat that is liberated when hydrogen is added across the double bond. For three molecules, the first one is cyclohexene, the second one is 1,3-cyclohexadiene, and the third one is benzene. We are also having a hypothetical molecule. What is a hypothetical molecule? Which do not have its original existence. We are just assuming it to be a molecule. Now all these compounds can be reduced to cyclohexane, as you can see. Now students, when we are going to add 1 mole of hydrogen in cyclohexene, the delta H calculated is 120 kilojoules per mole. Similarly, for 1,3-cyclohexadiene, since there are two double bonds, so we need 2 moles of hydrogen to be added and convert 1,3-cyclohexadiene into cyclohexane. The heat of hydrogenation is going to be the multiple of 120. So it is 231 kilojoules per mole approximately. Now if you assume a hypothetical compound, means all these three double bonds are isolated, then it should be a multiple of 3. 120 multiplied by 3 is equal to 360 kilojoules per mole. Now students, we are having a cyclic structure for benzene and having 3 double bonds, just like the hypothetical compound that we have assumed. Now the experimental value for heat of hydrogenation of benzene comes out to be only 208 kilojoules per mole, and the theoretical calculation is 360 kilojoules per mole, but the experimental value is 208. Now 360 minus 208 will give 152 kilojoules per mole. So you can see in the energy difference, which is making benzene more stable. So the amount of energy which is less is called the resonance energy than expected values. Students, keep in mind that the delta H of cyclohexatriene, a hypothetical molecule in which the double bonds are assumed to be isolated, is calculated to be 3 times the value of cyclohexene. This reflects that the energy we could expect to be released from 3 isolated double bonds. But students, you already know that the double bonds of benzene are not isolated. They are conjugated. And due to the conjugation and resonance, you can see how it has contributed to the stability of benzene. Now students, just for your better understanding, look at these chemical equations. This is cyclohexene. When 1 mole of hydrogen is added, it is converted into cyclohexane, a saturated cyclic compound. The delta H is 120 kilojoules per mole. Now if we are having a hypothetical cyclohexatriene, means having 3 double bonds, we have to add 3 moles of hydrogen to convert it into a saturated cyclohexane. The amount of energy should be 3 times 120. It is 359 kilojoules per mole. But when we have compared the theoretical value with the actual experimental value of benzene, it comes out to be 208 kilojoules per mole. So you can see the difference in energy values. By comparing this value with the experimental value of benzene, we can conclude that benzene is 152 kilojoules or 36 kilocalories per mole more stable than the hypothetical system. This is the resonance energy of benzene. Students, we have already discussed the structure of benzene according to molecular orbital treatment, and whenever we talk about reactivity, we have to consider the structure of the specific molecule in order to understand the site of chemical reaction. Students, let us look at the electrostatic potential of benzene. The image shows the electrostatic potential. The more red an area is, the higher the electron density, and more blue the area is, the lower the electron density. So note that the nucleophilic character of the aromatic P system is inside this region, the red region. Because over here you can see this is the sigma skeleton of benzene. And you know that the p orbitals which are in conjugation are perpendicular to this network. And they are just like a sheet of negative charge circulating in the center. So this is the area of nucleophilic character. In this way, students, the cyclic array of p bond is the region of high electron density. So arenes are typically nucleophiles just like alkenes and alkynes because they also have p system. Alkenes and alkynes are also nucleophilic, and benzene having double bonds also show nucleophilic character. But students, in benzene, unlike alkenes and alkynes which undergo addition reactions, why do they undergo addition reactions? Because they are unsaturated. They are having pi bonds. So any molecule can add across the double bond to convert it into a saturated hydrocarbon. But arenes typically undergo substitution reaction, in which the group, usually hydrogen, is replaced and the aromatic system is retained. Just look at this diagram. This hydrogen represented in red can be substituted in the presence of chlorine. So instead chlorine being added to the double bond, it replaces this hydrogen atom, and the stability of aromatic system favors the substitution over addition, which would destroy the aromatic system. Now if this Cl will be added over here, this double bond is going to vanish and benzene's stability will be compromised. So instead of addition over here, benzene prefers substitution, which is going to save the aromaticity or delocalization or the conjugation of this benzene ring, which is responsible for the stability of benzene. Here are some special features for the reactivity of benzene. Benzene is highly unsaturated compound. It has 3 double bonds in it, but it does not undergo addition reactions happily, as we discussed, because it is going to compromise its stability. The reason is that it shows resonance. The delocalization of 6 pi electrons make it extra stable. So for addition reaction, benzene requires more vigorous conditions than that of alkenes and alkynes. Students, let us study some addition reactions of benzene and let us see what are the conditions necessary for this addition. For example, catalytic hydrogenation. Benzene can be hydrogenated in the presence of catalysts like platinum, palladium or Rene nickel only at a higher temperature and pressure. Now you can see this is benzene. By adding hydrogen in the presence of these reagents, it is converted into cyclohexane, a saturated hydrocarbon. Similarly, this hydrogenation can take place at 100 degrees Celsius, 10 atm pressure, platinum supported on carbon. It is also going to convert into cyclohexane. Students, just like hydrogenation, halogens can also be added to the benzene. Benzene can add 3 molecules of chlorine or bromine under the influence of light. The benzene ring becomes saturated and we get benzene hexachloride and benzene hexabromide. This reaction shows that benzene has 3 double bonds in the ring. So students, if we are going to add 3 moles of bromine in benzene under these conditions, then it is going to give us benzene hexabromide. Each of the bromine atom is going to add across each carbon, giving us 1, 2, 3, 4, 5, 6 hexabromocyclohexane. Students, as we have discussed in alkenes and alkynes, that chlorine and bromine can easily give reactions under laboratory conditions, but the reactions of fluorine are very vigorous. Similarly, fluorine's reaction with benzene is very vigorous too, while that of iodine is very slow. So we can conclude that the addition reactions of hydrogen and chlorine with benzene shows that benzene is unsaturated because these molecules are added across the double bonds. It is unsaturated hydrocarbon and has 3 double bonds in it. Now students, we are going to study the oxidation reaction of benzene. Benzene is stable towards general oxidizing agents. However, it can be oxidized under certain conditions. For example, catalytic oxidation. When benzene is oxidized with air in the presence of vanadium pentoxide at 450 degrees Celsius, then we get malic anhydride. This is benzene when it is oxidized in air in the presence of V2O5 at 450 degrees Celsius. It gives malic anhydride. Now you can see C double bond O, O, C double bond O. This is anhydride. And it liberates carbon dioxide along with water vapors. Now students, this is the commercial method for the preparation of malic anhydride. Benzene is so stable towards oxidizing agents that it cannot be oxidized by using the strong oxidizing agents like KMnO4 and K2Cr2O7. The malic anhydride that is produced by oxidation of benzene, upon hydrolysis, it gives malic acid. As you can see, this anhydride functional group is converted into carboxylic group. So this is malic anhydride. Upon hydrolysis, it gives malic acid. Students, whenever a hydrocarbon is burned in the presence of oxygen, it gives carbon dioxide and water vapors. Since benzene is also a hydrocarbon, when it is burnt in the presence of air, carbon dioxide and water are produced just like other aliphatic hydrocarbons. So this is the chemical equation showing when benzene is burnt in the presence of air or oxygen, it gives carbon dioxide and water. Students, we have studied ozonolysis for alkenes as well as alkynes. Benzene also undergo ozonolysis. Benzene reacts with ozone to give glyoxal. First of all, a triozonoid is produced as an intermediate. Now, when ozone is reacted with benzene in the presence of KMnO4 as an oxidizing agent, triozonoid is formed. You can see the formula of benzene is C6H6, C6H6. When 3 moles of ozone are added each across this double bond, one ozone over here, second over here, and third over here, it is going to give you a triozonoid as an intermediate, which is an unstable structure. Upon reduction with zinc, it gives glyoxal. Students, let us study the oxidation of side chain. Alkyl groups, when they are present at the benzene ring, they are oxidized into carboxylic group. The oxidizing agents that we can use are potassium permanganate in the presence of sulfuric acid, potassium dichromate acidified with sulfuric acid, and dilute nitric acid. Now students, always remember this scheme that the alkyl group, whensoever is present, first the oxidizing agent is going to convert it into alcoholic functional group, then into aldehydic functional group, and then into carboxylic functional group. Although we are not going to study the mechanism for this conversion, but this is the scheme through which the alkyl groups are converted into carboxyl group. So these functional groups are produced as intermediates during the oxidation process. Students, concentrate on these chemical equations. This is toluene, benzene having a side chain and alkyl group. Now in the presence of oxidizing agents, it is going to oxidize its side chain and the benzene ring is going to remain as such. Now students, the process, the stepwise oxidation is that this CH3 will convert into CH2OH first, and then C double bond OH aldehyde group, and after that into carboxylic group, the scheme that I just told you. C double bond O, OH, and it is going to completely oxidize, giving benzoic acid. Now compare toluene with ethyl benzene. Now students, first of all, this CH3 is going to convert into CH3, CH2OH, alcohol, then aldehyde, C double bond OH, and then C double bond OOH, carboxylic group. But since this carbon is attached to a side chain still, which is this methyl group, the CC bond is going to break and the carboxylic functional group is going to further oxidize into carbon dioxide. So this CH3 group is converted into CO2. Now students, the second CH2 group will oxidize in the same manner into CH2OH, then aldehyde, then acidic group. But after COOH, it is not going to convert into carbon dioxide because now this carbon is attached to the carbon of benzene. And benzene is not going to compromise this bond because it is going to compromise its stability. Now you can see paraxylene as another example. Upon oxidation, it is going to give you terephthalic acid, 2 carboxylic acids upon oxidation. So benzene prefers to oxidize its side chain in the presence of oxidizing agents, and its ring is not going to compromise its stability. So it does not get oxidized in the presence of side chain. Students, we can draw this conclusion that when both methyl groups are oxidized and benzene ring remains unaffected, then it means that benzene ring is stable towards these oxidizing agents.